Okay, let's start over. It's good you only hear. Is it now? It feels like I don't know. Yeah, but also feels like audition or something. Okay, I gotta pretend it's more people. All right. Welcome to the fourth lecture on the lecture series on the future of AI, self-supervised learning and foundation models. Right. This is where we learn about the deep and fundamental revolution that's occurring within AI right now, where tremendous breakthroughs like ChatGPT is just the tip of the iceberg. Right? There's a lot of things happening, and here you understand what's happening and why. So today it's extremely exciting because we're talking about data. Begin talking a little bit about data because we haven't been talking about data enough, which is one of the core ingredients in actually understanding these models and build them yourself, right? And understanding where they can be applied. And also we talk about Stable Diffusion, which is, it's conditional image generation based on text. And it's extremely useful and powerful and very interesting in how it's engineered and built. And I think it gives a lot of insights into these technologies, and they put a lot of things together in a very fascinating way. So it will really increase our understanding and knowledge about these subjects. So what have we done so far, right? Well, in the first lecture, we had an introduction, and we went on a more high-level philosophical and historical journey about these topics, right? In the second lecture, we went through all the different algorithms. In the third lecture, last lecture, right, we went through ChatGPT in detail and learned about that. And what, a recurring theme kind of is that we, in self-supervised learning and foundation models, learn from observations, right? There's no labels needed. And that the meaning that we kind of get from this is very relational, right? We took this sample a few times about learning what a dog is, right? You don't learn what a dog is from a parent telling you what a dog is or from your feelings guiding you. You learn what a dog is from, observing dogs in different contexts, correlating and contrasting it. So a dog is something that's walked by an owner with a leash, right? It has an antagonistic relationship with cats, for example, and might catch frisbees when those are thrown, right? It's relational understanding of what a dog is by defining the meaning of a dog by the company it keeps. That's the essence of how we do self-supervised learning and build this foundational model that understands how the world works, right, and concepts within them. And also something that we touched on before, as we go now more to kind of detailed engineering and applications, right, is that AI is definitely successful because it gives up at fully understanding things, right? We just get better at being exposed to data and phenomena, and really we should kind of learn from that ourselves as well. And as you watch this lecture with a lot of details that we'll go through, perhaps, don't feel like you fully need to understand exactly what's going on. Focus on the intuition, right, and build some kind of familiarity and just expose yourself. So try to go with the flow. All right, so let's start with the first subject of today, data. So I think data might not be as sexy as applications and engineering, right? But I think it is, if you really understand it, and it's basically impossible to understand, the AI technology that we're seeing without understanding what kind of data that they want and need, right? And really, I believe that, the developments within AI and data are very kind of co-occurring. So every time we see a new AI or a new kind of breakthrough in AI, it also comes from a breakthrough in a new data. And not perhaps new data in the most straightforward sense, but a new perspective on data, right? And I think those are extremely important. And every time there's an algorithmic and engineering breakthrough, it comes from being able to see data differently and make use of it in a different way, right? Learning from data and observing data is the big breakthrough within self-supervised learning foundation models, right? And this just allows us to use more data and data in a different way and get at the meaning of data in a completely revolutionary way, right? And, so actually when you want to start working with these technologies, and when I work with a company in our startup, right, and we want to help them and they want to think about how to use AI within their business, actually data is a lot of times the place you should kind of start looking at. Understand what kind of data do we have, what data do we need to be able to kind of build up or track, right? And I think even in this course, right, we maybe should have started more focusing on the data early on in some sense. It's not as exciting perhaps to sell, but it's extremely, extremely important. And a lot of people take a lot of kind of shortcuts, they think, to just don't think about the data and only think about the certain applications that they want to achieve. But the data is somehow extremely, extremely key. And we talked before about the similarity, right, that we've seen kind of this tip of the iceberg in the recent breakthroughs with ChatGPT and Stable Diffusion and Dall-E and stuff, right? And then with that we have self-supervised learning foundation models as some kind of, below this, right, in some sense. And I think we can split this iceberg even kind of in a more detailed sense as well. So yes, we have these fancy new applications that happened in the last, few months, right? That are impressive and kind of really making these these subjects somehow much more generally known. But we've been doing, right, below this, and what this builds on is self-supervised learning and foundation models, which we've been doing now for quite, at least 4 or 5 years, right, in the same sense. And those are what we're learning about in this course, right, and it's kind of more important in some sense to really understand and to understand what's going on, right? But below this, in some sense, it's really, the data as well that we kind of forget about, but it's really, really key. And for a lot of these more public applications, both like Stable-Diffusion Dall-E and ChatGPT, they rely on the internet, right? That's their data platform or their database in some sense. And really, I think this is kind of, worth focusing on, because we talked about this a little bit before as well. 15 people spend 6 months building ChatGPT or something like that, right? Yes, that's very impressive, but it's very, you can reproduce that quite easily. But on the other hand, the internet is, billions of people spending 20-something years amassing all these different types of data, creating data, right, and putting in one platform that's accessible everywhere in some sense in this public domain. That's not, you can't recreate that by being 15 people over, a year or something, right? That's impossible kind of recreate. And, perhaps, right, the really impressive, the really most impressive aspect behind ChatGPT, right, might be the internet in some sense. Because that's what it's, you could not build ChatGPT without the internet. And having this, basically the greatest data collection effort in history is extremely, extremely useful. And if I had to pick which one I would want, I would definitely want to be able to have the internet, because I can recreate better versions of ChatGPT and kind of iterate on it, because this data is so extremely valuable, right? And somehow contains all of, big part of kind of, knowledge about the world, human beings, right, in some sense. So really, I think that that's overlooked. We focus only on the end product without thinking about the whole data that goes into it and enable this thing, right? And how the difference of ChatGPT and self-supervised learning, for example, is that we look at data differently, so we can utilize more of the internet and train on more of the internet in some sense, right? That's what also really makes this so powerful, because we make better use of this database, right, that we have. So with this being said, I want to encourage you to also start thinking a lot about the data and how data plays into this whole pipeline. And when you think about your own projects, and if you want to apply, right, these technologies like ChatGPT or improve on ChatGPT or Stable Diffusion, right, what kind of data would you need to kind of have or build up in some sense? When we talked about genomics, right, we have DNA because we can train on that, etc. What's the right data perspectives in different domains? I think that's a very useful skill to have, and we kind of haven't emphasized that enough. And right, we'd like to do a little bit of philosophizing in this lecture series as well, and I do a little bit of that just to give you perhaps an exciting idea. So we can perhaps apply this data-centric perspective a little bit more generally, right? And maybe even to ourselves in some sense. So I don't know if you guys know about the selfish gene, but there's some evidence suggesting that actually maybe the gene is the most important component in evolution, and actually the gene is what's selected for, and that us human beings are just kind of vehicles for the genes, right? And from this perspective, actually, maybe human beings and life in some sense are just data collectors for the genes. And And right, maybe the whole Earth and the biomass of life in some sense is like the internet with respect to genes, right? This is this great knowledge base with all the information, and that allows the appearance of intelligence and consciousness in some sense. This has this great internet in some sense, right? And maybe the most impressive thing is not our own brain, right, or human beings and our intelligence. Maybe that's not where the intelligence really exists. Maybe it actually exists in the Earth, generally, right, in this database, and the history of the Earth in some sense, right? And that's just kind of distillated into our genes. And right, so maybe if aliens actually reach Earth, I think we're kind of human-centric, but maybe they'd be like, we don't care about your brains, and you think you're so fancy human beings, right, intelligent. No, they just come and they just kind of try to collect and record all of our internet, which is basically the Earth, right, and all the life and organisms, right, and they just collect that, and they say, great, we have the database, now we can train brains and different versions of brains that we want to, right, because all that is instilled in the data, right? They rather want, you rather want the internet than ChatGPT, because the internet you can build improved ChatGPT versions, right? It's all kind of, within that data, and maybe the data is the really important things, and not the small agents that have learned to, navigate in it. Maybe the data itself, in some sense, is the really interesting part. Yeah. All right. So that was just a little bit of a digression. So let's jump into our main topic. Conditional image generation, right? Where we go from text prompts to images. And perhaps the most well-known examples are Dall-E and Stable-Diffusion, right? Here are two examples side by side. We have Dall-E at the left and Stable-Diffusion on the right. And here we write a high-tech solar punk utopia in the Amazon rainforest. I actually don't know what solar punk is, but it at least looks kind of reasonable, right? Or fairly similar. It looks like real images, realistic, and it's very hard to tell it's actually a computer created these, right? So it's very impressive. And we can also take the example of the image I just showed you, because basically I created all the images in this lecture series by using Dall-E. And the prompt here I wrote was a globe covered with DNA sequences wrapped around it, and digital art to get kind of the theme. And this is what it spit out. And actually getting good prompts is quite hard. You need to have some understanding to really start doing it well. And it helps even to understand self-supervised learning to be able to write good prompts. And apparently, you can even sell good prompts on the internet and stuff and get money for it. Anyways, of course, video is just a sequence of images. So now Google has done this image and video where they can go from text prompts to actually videos of that text prompt, right? So it's also extremely impressive. And of course, it's just getting better and better for every month that we work on this, right? Okay, so now we want to think about how to design these systems ourselves, right? So what is important actually that we want to accomplish? Well, of course we want high image quality. We want high image quality in terms of pixels and resolution, but also we want images to look real, coherent, reasonable in our own kind of human expectations, right? We also want to have a high language and image correspondence. So when we write something that's kind of unique or new, we want the model to be able to be creative enough to actually generate that, whatever we might ask for, but still look realistic and kind of reasonable, right? And tied into this as well, we want to have a great variety of images. Basically, we want to learn the full distribution of images that we care about. We might want to say that we might want to be able to generate a dog, but we don't want it to generate the same dog each time. We want to be able to generate all possible dogs, because that really shows that there's a full understanding somehow of that concept. And of course, we want it to be fast to train and use. And what we'll see basically is that most of these we'll solve using good engineering and good technology, and we won't focus as much on this language and image correspondence, because that's just more about the data. Because if we just, it's just, what we'll need to do that well is just to have actual data with correspondences between language and images, and we can utilize pre-trained models to rely little bit less on the data, but that would be more a data question, because in this application actually we will need to have good text and image correspondences in data to do this well. So that's how we're going to solve that. So there will be a little bit more of a data question we won't really dive into. But we'll get that from the internet as well, but it will be a little bit more kind of a data question than engineering. All right, so what we care about, right, is generating images. Then that's a core kind of challenge that we'll focus on, and it really is the core challenge, and we're working for quite some time. And when we're able to generate images in a good way, realistic images with a great variety, right, then adding the language component will be just having that data that connects them in some sense. So we'll start talking actually about drawing faces as our first dive into understanding how to generate images. Just how do we draw faces? How would we learn to draw faces, right? Here we have some examples of something or someone who's able to draw faces fairly well. We'll think about how we can judge this, right? But it looks good, right? But let's say we have some model that we want to evaluate. What if we train this to draw faces, and each time we ask it to draw a face, it draws the same face? How good would we kind of say that this model is, right? It draws a face, but the same face every time. Can we really trust that it has a good understanding of drawing faces generally? Can we kind of see it's a good kind of artist in some sense that has creativity and the ability to understand all the nuances of faces, right? It's very doubtful that we would if it only generates a single face each time, right? And it's not even very useful, right? It's just literally memorize something and shows the same face perhaps each time, right? How would we use that? I mean, if we can draw a ton of different faces, we could create different characters and stuff, right? And we could actually make it more useful, but this doesn't seem to be too useful, right? So, and this actually goes now into one component about this has no input perhaps, but no input, you can think about it as having the same input at each time that we evaluate this model, use this model, right? Basically, no input is the same input. So maybe also we're just being stupid because we expect different results, with the same input, right? So doing the same thing over and over again, and we expect some kind of different results. And that's actually kind of true because it's something that neural networks have a hard time, creating themselves is randomness, right? And you can think about these neural networks right now as deterministic functions. So if you give the same input, they will always get the same output in some sense. So we really have to help the model along and give it some kind of randomness that it can use as a base to be creative. It's like, maybe for us as human beings, you can imagine that if we, we maybe get a lot of, different random inputs by just, sometimes you say like change the scenery and you'll be more creative perhaps. But I think we get different random inputs all the time because we can never recreate exactly the same environment. But also, right, if we just would focus really, really hard on recreating an environment for some person, they would probably react in a very similar way each time. But it's just really, really hard. But for these ideal neural networks that are on a computer, actually, they're mostly just run in the same environment each time on this computer. So we somehow have to fake the change in environment by adding and giving it some randomness that it can use to create a variety and diversity. So what we'll do now is that we'll say that, okay, we're gonna feed some randomness to the model as some input, which then could allow it to give different output because it gets different input, right? So at least here we can expect to make some improvements because now we're actually giving different input that the model can use to map to different output, right? Even if it's this deterministic function, it now can show a much greater variety of output because the input is different, right? And to do this, right, we want to be able to get randomness somehow, right? So we want to be able to sample. And actually it turns out that, if the randomness is defined in a fairly simple way, a computer can generate randomness, right? We can think about it just as picking on this, tons of different random pixels in black and white and stuff, right? We can just think about taking some different squares from there, right, and feeding it in somehow. So, but we want to be able to have a setup where we can sample randomness via computer, right? So we can run this and do it in an easy way. All right, so this is great. We've now at least, solved the issue of we can allow a model and a brain and a computer, right, to generate a diverse set of samples with a lot of randomness to the process in some sense, because we sample from some randomness. So we help it out. We give it some randomness so it can replicate the randomness in terms of its output, right? But let's say now that we want to draw an image, right? Another aspect is basically, do we really want to distill all this randomness that we get into a single image at one go, right? Maybe it is easier if we can start drawing something and then we can improve on ourselves, right? So the model gets some randomness here, and it basically removes some of it, right? The top here, top right, and it starts with the head, top of the head, right? And then it can basically say, like, I've done this step, I don't have to do everything in one go. Now I'll take that as an input, and I'll say, like, well, now at least I know the start, from the top a little bit in the second row, and I'll just do 1/3 more, and I'll create the eyes and the nose, right? And then I say, like, great, I'm here, and I've had now 2 attempts, and then at the very last attempt, I'll just like look at the very top, bottom row here, and I'll finish off with the mouth, etc., right, etc. Maybe this is actually very useful for the model to be able to kind of improve on itself, so that it doesn't have to do everything in one single go, right? If you would draw an image of something, it's very hard to imagine, right, that you would just like, oh, this is actually how it looks like, and you basically finish it super, super quickly and almost everything in one single go, right? You start somewhere, you trace it out perhaps, and you add things, and you iterate on your own, project, right? So this is kind of definitely ties to our own human intuition of how we would do this creative process ourselves in some sense. It's helpful to be able to do this in multiple steps and start, with some idea and then trace it out and be able to update in some sense. You don't have to do it perfect at your first try, but you can try again and improve on it. So it's somehow that we kind of may believe is a really helpful bias to be able to improve on yourself. So it turns out that it actually is really, really useful, because it's useful for ourselves and as for a model to be able to start with the process and then basically iterate on it. It's going to be much, much easier for it. And also, it's very helpful not only in terms of when you actually want to draw something, but also when you want to learn to draw something. It's very useful if you have these kind of different levels. Now maybe hard, medium, and easy is not the best word to describe this, but at least you have kind of different levels of the training process. So if we're able to generate this data for the model during training, in some sense, that you want to learn to draw, when it gets like different levels of difficulties in drawing images, right? It's very useful, because then maybe it starts off, very, very bad at drawing, but it can just start getting some, making some progress on the very easy examples. And when it gets better doing the easy examples, it can perhaps move on to doing the harder, medium examples. So really it helps as well to have this diversity of examples that are from hard to from hard to easy in some sense, because that allows the model to learn, much more robustly and faster, and also just learn in general. Because otherwise, if it only has hard examples, maybe it's too hard for it and will never learn anything, because it just struggles and doesn't make any progress, because it just flies over its head, right? It's just too difficult. So it's also really, really good for training. It's actually able to see a different kind of level of examples in this sense. All right. So this was, a quick attempt to just give an intuition here a little bit about things that we now try to, make more detailed. But it turns out, as summarized, when we work with new networks, they're basically deterministic functions, really flexible deterministic functions, but they cannot create randomness by themselves. So if you want to be able to generate, a variety of faces, we need to give it some randomness that it has a starting point to map to random different faces. So we need to be able to have some noises input that we can sample from and feed to the model to actually get a great variety of different faces. Also, creating everything in one step is hard. This is actually shown, we'll talk about it empirically, it's hard when we try to do it. And also, it perhaps makes sense from our own human experience that we want to be able to try and improve on our own output in some sense. And right, and something that we saw here perhaps as well, if we want to be able to improve on something iteratively, right, and if this noise is our input in some sense, we want the model to be able to take in some input, generate some output, right? That's a better version in some sense, where we remove some noise at least, or we make some progress, and then we want to be able to feed that into the model again. So somehow the model needs to be able to both input, it needs to be able to input its own output to be able to iterate, right? So that's also, so somehow, if we call that kind of incomplete process noise, the noise that is able to, the noise needs to be able to be part of both its output as well as its input in some sense. We'll talk more about that. Right, and we need to be able to handle different levels of noise in some sense, if noise represents incompleteness, because as we move on and complete, we do a small step each time. We need to be able to know what to do at each of those different levels. We need to go from a very incomplete, noisy version to make a small progress, right? We also need to go from a very almost completed version to add all the different details, right? Whatever those might be. So we need to be able to handle all these, differences in terms of noise or something being incomplete. So a lot of these insights actually come from a extensive work on trying to generate images and faces. And the approach that we used for this in the field, that was really successful was GANs, so generative adversarial networks, right? And they got pretty far, but they had these failure cases that we talked about. I mean, first off, we talked about this before, right, in the second lecture, but in a GAN, we have this artist that gets one chance to generate a face, right, in some sense. And then they have a critic that's also trained at the same time, and the critic is trained to say, okay, which one here, because we have a data set of faces that we just have from the internet, and then the critic is supposed to say, is this a real face or the artist attempt at creating a face? And as the critic gets better at discerning it, the artist needs to get better at creating realistic faces, because it needs to fool the critic, right? It needs to make the critic happy and make the critic believe that actually this is a real face. So when they learn together, they can both become really, really good, and we can get an artist that's really, really good at generating realistic faces, right? But actually this the progress here stopped because, first off, it turns out that it's actually very, very hard, because the artist here has just one single try. It just has to generate a complete image and then feed it to the critic. It doesn't get the chance to improve on itself. So that's very hard to do in a GAN. So it gets, you can try to do similar things, but it gets much, much harder in this sense. And the artist and critic are also very, very hard to train, because you want this, as you said before, a different levels of difficulties in some sense. So you can start being a very, very bad artist to becoming better and better, right? In this sense, the artist and critic need to develop in a very, very similar way. Because if the critic gets too good, then the artist can never, the input that gets from the critic is just too detailed, perhaps, to be useful. So if the critic is too good, the artist won't be able to catch up. And as well, if the artist just gets much better than the critic, but not very good, but just much better than the critic is just confused, and it doesn't know the difference at all, and it makes no headway, right? So this turns out to be actually real problems when we try to do this, right? And that's why we addressed it. All right. So, of course, we now had this very simple example of noise that we kind of draw something from top down, right? But the professionals, they don't draw that way, right? They start more like this, where we draw the outline of something, and then we perhaps iterate on that and move on, right? So somehow we decide on the shape of the head, then different proportions, and we get more and more towards detail as we have made decisions about the bigger picture first, right? So maybe actually this is a much, much better process to think about, improving on yourself, to go from outline to details, right? Rather than just going from top to bottom or something like we tried to show before. So this is something that perhaps is what we really want, to encourage, and it's actually very, very useful in some sense, to be able to start out with the outlines and improve on ourselves and get more and more to the details. So this is what we'll talk about, and this is what diffusion tries to get at. And I think another intuition around this is actually it's much, much more simple to point in the right direction than to provide the exact coordinates of something, right? So if I ask you, for example, where this place in Uzbekistan is, right? You probably have a very, very hard time providing me with the exact location, but you can probably point in the right direction somehow, right? So if we're in the East Coast, we can point in the right direction, take a step towards Europe or something, right? And we'll get closer. So you might not, we might not know the exact location, but we might be very easy for us to point in the right direction, and that's somehow, much more conducive to actually know if you're making some progress. Like, well, we're pointing in some direction. Yeah, you're in the right direction. We move towards there, and then you can, also get a much stronger signal as you try to learn where Uzbekistan is and how to navigate. That we somehow, get a feedback on are we going the right direction rather than do we have the exactly right coordinates, right? There's also like very, very difficult feedback to use. Like, well, we get some coordinates, and then we say yes and no. It's also very hard to make progress. But if you can point in some direction and people say, yes, that's the right direction, it also helps you to navigate perhaps better in some sense, right? That's also why if you ask for directions, not the exact coordinates in some sense, right? And it's also where these experiments with 6 degrees of separation, right? So if you ask somebody, you ask somebody in America to find some person in Uzbekistan, it typically takes at most 6 people to find that actual person or location. So the experiments, they'll get in America a letter, and then they get to send that to a new address, right? They can't Google it, they just have to send it to a new address, and then it repeats itself, right? So basically the person in America will send this letter to somebody in East Europe, and then they will send it along, etc. And somehow it only takes 6 steps at most to actually find exactly the right location, because we all have a sense of direction. And it's much easier to talk about direction than the exact destination in some sense, which I also think is a good intuition for why, diffusion and being able to go from an outline to details is very, very useful, and also very good for our creative process as to learn to do something well, is actually doing it in steps. So, this is what denoising and especially diffusion is, right? And we talked about this in the second lecture, that we call this a game of denoising, right? But what we do is we start from something that's, in this sense, pure noise, but we're able to take a small step in the right direction. So we're able to denoise it and decide somehow from pure noise the outlines of a face, right? We take now a step and remove some noise, and we get at the very kind of high-level contours. And then when we've done that, we get it as a new input, and we improve on it to get more details, right? Make a further step in the right direction towards the face and make decisions about how this face is supposed to look like. And then, right, we keep going in this sense, right? And this is exactly, right, denoising is a single step if it's removing noise, right? Making decisions around how the details actually look like. And diffusion is basically this process of iterating on that, right? Composed steps of denoising is diffusion. And here we have 4 steps or 3 steps, right? And we can run this until we're happy in some sense. Okay, we're happy now, it's good enough, and then we stop. All right, and of course, we also want to be able to do this, conditioned on language. You want the language somehow to guide us in this process in diffusion, right? To denoise things, so we can make denoising decisions, but guided by the language. That's why we also, need to have these correspondences between when we train actually, right? But we basically feed this language to the model as it does this to allow it to make decisions based on this conditional language input. And of course, we don't have to learn language from scratch. We can use one of our language models that we've talked about before, maybe a ChatGPT-like model that we can embed language with, so we don't have to learn language from scratch, perhaps. That's also very helpful. All right, so what you're looking at now is basically the core approach behind diffusion, denoising, right? So diffusion, stable diffusion. Diffusion is just steps of denoising, and it's all about the good kind of useful inductive bias of being able to look at the outlines and towards details, right? And that's good both for the process when you want to generate images, but also it's good for training, because now you get a variety of different training samples that might go from just tiny noise to a lot of noise, right? So it's different kind of levels. So this is, most of the intuition around stable diffusion is what we just talked about. But now we're going to go in more to detail to kind of understand what's going on. So we'll talk about how we create the training data, which is going to turn out to be important, right? Because we want to be able to create training data without human beings or human experts in a loop. Then we talk about how we train the model, how the model is then used, and then we'll end up with some details. And we might go through this fairly quickly, so don't worry if you don't get everything. All right. So we now, said that it is useful to have these degrees of, granularities of outline versus details, right? And this is a great example, right? And this is literally perhaps from somebody that wants to teach somebody about drawing faces, right? Because now we can say, okay, we can learn from this. We can try ourselves to go from outline, and then we can see, we're making the right kind of progress, right? We can try to go from the first picture to the second pictures, and we learn about doing the outlines, and then we learn about the details. So these are complementary skills in some sense, right? So this is a great example, teaching example of how to draw faces. So you want to be able to get the same kind of training examples for our model to learn from, right? But this, of course, is done by a human expert. And we don't want human experts in the loop, so we can't, we cannot get this data ourselves. We cannot look at all the different images and visual concepts and then have a human artist to say like, well, I'm going to create, 10 different perspectives on this image from outline to details, right? That's just too expensive. We don't want an artist or experts in a loop. We want billions of examples, not 10 examples, right? So we need to think about how to do this similar thing as close as we can do as possible by just, using the internet and computers, right? So that's what we do, right? So we now, that's why we use the denoising process, is because we can now get images from online. So we get basically an unlimited amount of images that we can download. And then we can have a computer generate this Gaussian noise, so normal noise. Just like it generates this noise image that we see here of random pixels, and it can do it at different levels, right? We can basically tell us how intense we want this noise to be. And then we basically superposition or add this noise to the image to get this input and target, right? So the input corresponds to this different granularity, right, of noise, outline versus detail, right? And then we have the target that we know that we want to be able to reach at some point, right? So this is a very good way now that we can perhaps at least replicate this process of getting outline to details, right? Because we can add some noise, get the input, noisy version, right? And then a target that we want to arrive at some point. And of course, as I said, we want to have different granularities of noise, so we can do the same thing with the same image, but add different types of noise. Like less noise, so it also focuses more on details, right? So as more, and the input has bigger proportion of the image in some sense, right? Less noise, but now can perhaps do a better job of actually replicating a target in some sense. We want these different granularities. And also, of course, we want to be able to create images, from thin air, because the user is not going to provide us with a starting point. So we also need to feed pure noise, right? We need to be able to generate pure noise and then have a target so we can start to be creative and generate images from just pure noise. So we don't have to have a noisy image as a starting point. We can just go from pure noise that we can generate for free and then make progress toward a target. So this is how we're going to look at this training data in some sense. But also, as I said before, we're just going to not talk about it a lot, but we're going to assume as well that we actually do have a lot of examples where there is a text prompt that actually will describe the targets. So that now the input can actually, or the denoising and diffusion process can be guided by the language, right? Which allows us evaluation to actually just provide only some text and then generate an actual image, because that's more useful than just randoming, than just creating random images. It's more useful to be able to guide that by providing some language. But the process is just basically the same exactly, just that this requires more detailed data that actually connects text with images. All right. So basically how this turns out to work is that we're going to give now the model during training, right, both a certain image with a certain noise level. And we want it to do its best guess of, and some language, right? And then the model tries to kind of remove as much noise as it can, right? And then we're gonna compare this with the target, because we know the target, right? We hide it from the model, but we know the target. So then after it's done its best attempt at removing as much noise as it can, in some sense, we're gonna compare its performance, right, or its output with the actual target that we know about. And I won't go into details here, but we basically say that we're gonna give kind of directional feedback, saying like, hey, you went in the right direction. You don't have to be, perfect and close, but you went in the right direction towards the target here. And that's the core feedback we're going to give, right? The model is going to get something that's fairly noisy, and if it's very noisy, as long as it points in the right direction, it gets some positive feedback, right? And it gets that kind of nuanced feedback. It doesn't have to be perfect, it just has to make some progress. So now also it can learn from these different granularities, right? That if it gets something that's super, super noisy, of course, it can't guess the exact picture, but at least it makes some progress. It's doing a good job in some sense, and it can get better and better. So now we're going to propagate that feedback to the big neural network with a lot of parameters, and they'll adjust itself to become better and better as it sees tons of examples, right? And then, of course, when we actually use this, we get the prompt, a man's face, for example, and the pure noise from a computer, and then we now iterate this process multiple times in evaluation, right? Because we have now a trained network, a trained denoiser, that's trained on different noise levels. So basically, whatever it outputs, it's also kind of expected that it's seen something like that during training, right? It knows how to handle different noise levels, and since it removes, a little bit of noise each time, it basically generates itself a new image with a lower noise level. And then it's been trained to handle that as well in some sense, right? So you can run it on its own output. So you run it on its own output, and it improves at each step here. And then you can decide, well, at what point do we think we have something that we're happy enough with and we can output, right? So it is, this is perhaps something you need to think about, but it's very good, because now when we actually use it, it can work as long as we want to improve on itself, right? It's able to start off with the outlines and then add more and more details each time it sees its own output as input. And it can decide, well, I'm going to focus on the outline first, and then add and make some decisions later on. So it doesn't have to make decisions about the details of the mouth. It doesn't have to make decisions about what type of beard it should have. It can start just focusing on the outlines of the face, and then it can say, well, will it have beard or not have beard, right? And then it can actually go in and focus on how does that beard look like. So making these hierarchies of decisions by being fed its own output is extremely, extremely useful in evaluation. But also it's useful during training, because that allows us to focus on more kind of, if you want to say, easy versus hard things, and learn in a more efficient way, right? It's like when you teach a kid to draw, maybe they can draw by themselves, but they can also follow these outlines in drawing books and stuff, right? So you want to be able to give a variety of different levels, and hope that the kid will be able to learn, because it has a variety of difficult levels in some sense. So it's both useful for training as well as evaluation. All right. So again, now we went a little bit more into detail, right? And you've had now even more understanding of how Stable Diffusion works. And again, you have most of the intuition and feedback. So we won't stop here. You can stop wherever you want to, but we'll go on a little bit into even more details for exactly how that engineering works. And of course, a lot of these different things that we talk about now is conditioned on the availability of hardware and technology, right? And maybe this will change and it definitely will change, and we'll use different techniques and stuff, right? as we learn more about these things. But let's dive a little bit more into details on how Stable Diffusion does this. So one, and also Dall-E and everything else that we see in image generation uses the same process of diffusion. So this is helpful everywhere. But more unique to Stable Diffusion is that they actually say something that's quite interesting, and they claim, right? They don't perhaps prove it, but they say that in images, there's a lot of repetitive details. Like, so if you look at this face, right, or the outlines of a face, it has a lot of, pores and stuff, right? And it's very repetitive in some sense. It's like a wallpaper almost, right? Like, it's not a lot of big outlines. It's like the details are very repetitive and maybe not very hard to draw, right? You can just, it is repetitive pattern in some sense. So that's something they say, like, well, actually, in natural images that we care about, details are very repetitive. Like if you look at your table or your floor, it might be very repetitive. But for diffusion, it actually takes a lot of time. And maybe we shouldn't focus so much time and compute on the details. And that would be nice, perhaps. And diffusion is perhaps not. Diffusion is quite expensive because you run on your own input several times. Maybe we can use something else for the details and let diffusion focus on the bigger picture a little bit more. So, right, since the denoising and diffusion works on the level of pixel, resolution in some sense is very expensive. So if you want to run denoising and diffusion on something that's 1024 times 1024, that's 1,000,000 pixel, right? But if we can make the dimensions 8 times smaller, we get 64 times fewer pixels. So that'd be kind of a great, time saver if we can actually run diffusion and denoising on these smaller images and save a lot of time and compute, right? And maybe we can still kind of focus on the bigger outline and bigger perspective in this smaller image, and we can let somebody else take care of the details in some sense. So it's exactly what Stable Diffusion decides to do. And then they think about something that we talked about earlier, which is this game of denoising, right? Game of compression. And this is what we talked about, going from some input data, running it to some bottleneck to get a much more compressed version of it, right? And then be able to use it to kind of recreate it. So we just compress this image now to some small vector that contains the most important information, because we want to be able to use the same information to kind of recreate it, right? Talked about this. It's called, right, Why, I mean, the smart thing here as well with Stable Diffusion is that to say that this compressed representation in the middle doesn't have to be a random vector, right? What if it just is a smaller version of the image itself? Like, what if we train this now to actually create smaller images and use technologies now that are good at handling details, so we basically learn to compress this in a very reliable way, right? And this, of course, as we talked about, is called auto-encoders, and we'll split this up now for utility of having encode and decode part, right? So encoder goes from the big image to the smaller image, and the decoder goes back, right? And we're not going to assume that actually this is trained and works well, that we're able to go from a big picture to a small image and a small image to a big image, right? Using these two new brains that we have, or models. And let's assume their train actually works great. Here, I mean, they don't work perfect here, but let's assume they just work really, really well, and we're happy with them. So what does this mean, right, if we have that? Well, it means now that we can basically just think about new images that, in a new image space where everything is much smaller, and we can then apply our denoising and diffusion to this much smaller space. And given that the encoder and decoder works really, really well, we're basically not losing anything. So this, of course, we haven't just talked about how we get the encoder and decoder, but if we're able to go and translate images, big images to small images, and small images to big images without losing anything, we basically replicate our problem in a much smaller space. So now, right, when we train this in this new setup, we're gonna have these big images that we get from the internet with high resolutions, right? We're gonna encode them to look, to get a smaller image that has more of the important aspects and maybe misses some of the details, but that's fine. Then we're gonna, add noise now to this. We get a new target which is in this smaller image space. We now add noise to that to create this new input, right, that we talked about before, but we do it in this smaller space. We now feed this forward, right, and we apply denoising here and train the model here, right? So we get a prompt to the image, and we feed it to the denoiser as well as the input, and we get a guess of what's the right direction, how do we make progress, how do we remove noise. We compare it to the target in the smaller space, and we propagate that back to the denoiser to make it better. So now we just train effectively about in the smaller space. Now that we have the encoder, we can shrink images without losing much. We can now train the denoiser and using diffusion, right? And the denoiser doesn't even need to know about that there exists some bigger image space, right? It just needs to get these pairs, and it does. So we can now apply the same process within this smaller space. And of course, here we use the encoder, but when we actually use it in production or with users, we have some user ourselves maybe types onto the website a man's face. They can generate pure noise very simply, right? And then you feed this to both of these to the denoiser. It starts making steps in the right direction in this smaller space, right? As we start off, it's efficient, it's fast in this smaller space. It goes on for this different number of steps, which is expensive, right? Maybe it's 10,000 steps, and we can do it in a smaller space, so we're like 64 times faster than we would have been otherwise. And then when we're happy here, we feed it to the decoder that we have. It's able to upscale the image, add all these different details that are repetitive, and we get a nice image that's high resolution that we can feed to our user, and he's happy. So that's actually how Stable Diffusion does it, and it gives a lot of benefits in terms of training faster and evaluating faster, right? And you can then run for more number of steps with the same amount of compute than you would do in this larger image space. So this, I think, is also the core kind of approach for Stable Diffusion. And now you know the secret sauce within Stable Diffusion, but we'll add just a little bit more details, for completion. So we talked about this encoder and decoder, and how do we train this now, perhaps, and get to something that's really, really good? And I'll go through this quite quickly as well, so you need to understand everything. There's going to be a few different concepts involved. And we could, of course, just train it in a more straightforward way, but they decide to do something quite interesting. And of course, they are experts, so they're going to combine things using fancy engineering, right? Because they have a lot of expertise. And this approach as well might change as we get better and better kind of procedures, right? But how do they get these great encoder and decoders, right? It's definitely part of the pipeline of Stable Diffusion. So how do they accomplish this? So as you said, right, we have this auto-encoder setup where we have an image, right? So now when we train this, right, we just get images from the internet, and we train this encoder to generate a smaller image and then go back to the original space, right? So we have an original image and a recreated image. And we now want to be able to say, basically, and communicate. So one of the core concepts here, and problems is how do we communicate similarity, right? Because we want to be able to say, basically, is this model doing a good job? What is actually similar, right? What kind of distance do we care about to compare this original image with the recreated image, right? Because we want it to basically lose no information, so we want the recreation to be as close as possible to the original one, right? But how do we communicate that? What is actually being as close as possible, right? What is similarity in distance in this sense? So what we could try first, right, is to say that we're just going to compare pixel to pixel. So we're going to look at the original image, we're going to feed it through these models and get the recreated one, and we're going to compare pixels at the same locations. So we just take two different patches here at the same locations, and we look at the L2 loss, so there's the difference between them. And if the difference is small, we're happy. If it's big, we're unhappy, right? And this might make sense because if the recreated version, right, is exactly like the original, then it's going to be zero loss, right? So it makes sense perhaps from that perspective, but also here, right, where images are at least a little bit similar, but they're shifted a little bit, and we compare the eye with the eyebrow, the difference is going to be huge in terms of pixel, even though they're quite similar in terms of both being, faces of a man, right, with similar features. So somehow the pixel-to-pixel comparison is just too detailed, right? It's not informative enough, and it doesn't have a kind of a hierarchical level of how it communicates similarity. It's just too, and also it's going to be hard to learn from as well in this sense. So that actually doesn't work well at all. So they're gonna do something interesting now. They're actually gonna use this GAN setup, so generative adversarial networks, that actually turns out empirically to work well at generating details. So they're gonna now give these two different patches to a critic that's supposed to be able to say, is this patch from the original image or from the recreated image, right? So it's trained to discern them, and the encoder and decoder is trained to fool it. So the encoder and decoder is supposed to, go to this smaller image space and then create these patches now in the recreated space, so the critic doesn't know if it's from the original image or from the new image, right? So as the encoder and decoder gets better, the critic needs to get better, and as the critic gets better at discerning them, the encoder and decoder needs to be better at actually generating realistic, recreations. All right. So of course, this is what they do, and it works well on this patch level. So they do this for, they split up the image in different patches because these GANs are good at detailed information, comparing, patches. But they're not good at comparing big things like the whole image. So that then say like, well, they need something else to do that. So it's also quite interesting, because this is where, when we think perhaps about the bigger picture and comparing more high-level features between these two different images, right? Since the end user here, in some sense, right, it's going to be human beings. We're going to be the one that use this, whatever product we output, right? We're going to use them, so they want to have some, similarity based on human intuition and human perspective of similarity, right? When we see two different images, we have a fairly clear sense that if they're similar or not, right? And we have it on perhaps multiple levels. And of course, similarity at the very end here is going to be judged by human beings, because we're the end users typing things in. So they want to have something now, a distance or some understanding of similarity that conforms to our human understanding of similarity, right? That would be very, very nice, because at the very end, human beings will be the ones using it. So how do we get this, right? I also think this is very interesting because it ties back to our previous lectures again, because one way to learn similarity or representation of visual concepts is through self-supervised learning, right? Where we perhaps do something that we talked about before, contrastive learning for images, where we define similarity based on co-occurrence, right? So in contrastive learning, we say that concepts that appear in the same images or in the same companies are similar concepts, right? So here, the model, the embedder, I call it, right? We train a model now using contrastive learning to embed and create latent features for these visual concepts. If it gets this during training now, it's supposed to look at this, image where you have this human being that walks with a leash, right? That's a crop. It's supposed to push that representation closer to the dog, right? Because they are part of the same image, and then further away from the woman and the cat, right? And this makes sense, right? In some sense from a human perspective as well, because an owner that walks with a leash probably is more close and similar to a dog, because that's what it's probably walking. You don't typically walk your cats with leashes, right? So this makes total sense, and if you do this on enough images and data, you'll get a really powerful kind of nuanced vectors and latent features around visual, images, right, and crops. And I think it's very interesting because actually what research shows is that when you train this, this procedure on a lot of images, and you then compare the distance in the features that you create, right? So you take two different images, you look at maybe you take 5 different images, and you say which ones are close, which ones are not, and you judge that based on this embedded model. That you compare the output, right? So these vectors, latent vectors, and you compare the difference. That corresponds actually, in studies, very closely to how human beings think that things are related or close. So if you ask this model, are these two images closer than these two images? And it will correspond very, very accurately to how human beings typically judge this in terms of similarity, which also is another evidence that actually we probably as well use self-supervised learning to, learn about visual concepts in the same way, because this corresponds surprisingly well to our own intuition. So that's what they do. They now use a pre-trained model that's trained using contrastive learning, right, to embed these images to a latent space, so vectors, right? Vectors that have now semantic meaning, right? Different numbers of semantic meanings that we talked about before, and it now tries to minimize the distance in this new latent space, which then corresponds to minimizing distance more in our brain space that corresponds to human judgment of similarity. And that's how they get at the high-level comparison. This doesn't really work well on details like just pores. It works well on bigger scale. So they combine both this embedder to get the global outline and the kind of general features, and then they do the GANs on getting all the different details. And it works really, really well. And that's, of course, empirical, because it could be the case that these two different losses, right, work against each other. Who knows, right? But empirically, it shows that it actually works. They converge to something that works extremely, extremely well. And yeah, and then we get a really, really good encoder and decoder, so we can work in this smaller image space and apply our diffusion. Okay, so now we have covered all the details in Stable Diffusion. So to summarize a little bit, right? Denoising can create, from pure noise, so basically from thin air. That's how it's created, and can basically hallucinate almost these new results for us, right? Right, diffusion, just know the terms, is just iterative denoising, right? Where you allow to improve on your own output, but in order to do that well, right, you need to see different levels of, outline to details examples during your training. And also it helps training, right? And of course, we can condition this on a language input, but it requires text, prompts, and image correspondences that are actually good. So we need to get that from data. So we need some smart way of scraping that from the internet. Diffusion and denoising is expensive in high-resolution images, but we can do it in a compressed image space by training these auto-encoder pipelines. And when we create these auto-encoder pipelines, and maybe in general, it's very interesting to see that we need to think about similarity in image space, for example, and distance from a more structured approach, and try to mimic our own human intuition. Because at the end of the day, we are the human beings that are supposed to use it, and we're going to be the one judging it. So we want to be able to make humans happy. And I think it's very, very cool that actually, right, in this approach, we used a language model already trained to embed the language. We used denoising and diffusion, right? We used auto-encoders to get to a smaller image space where denoising and diffusion, works better and it's more effective. We use GANs still, right, to train this autoencoder, and we also use the contrastive learning image embedder to train this autoencoder, right? So these are like tons of different algorithms that we talked about in the second lecture, and all put together here to squeeze out most of it, and really, right, that we can apply them here as well, because they're all within self-supervised learning and foundation models, so they don't need to have human expert data, so we can combine them together as well and train them in a similar way in some sense, because they are fairly, or they are fundamentally very similar. Also, right, I think one other thing is cool about doing this, in self-supervised learning and foundation models and AI in generally, is that it kind of corresponds more and more to our human intuition. And actually, it's very, very amazing. You can sit down and think about, how do you draw images? Now, how do we draw images? What's a useful inductive bias? Is it useful to be able to iteratively improve on yourself? Is that part, perhaps, of the creative process? Is external noise and diversity also part of your creative process? Do you need to expose yourself to new experiences to actually be able to learn new things and be creative, right? And I think this also, this, of course, is corresponds now as well to what we're actually seeing. And it's very fascinating how both that understanding helps us to improve the AI and the output, right? And that in turn helps us understand ourselves in some sense, because we can try to recreate our own abilities, and that allows us to understand our own abilities better as well. All right. We also talked about, this iceberg, where we have the fancy things that we talked about in the last two lectures, like ChatGPT and Stable Diffusion, right? But that the underlying technologies here, and that's really causing this revolution that we'll see everywhere now, is self-supervised learning and foundation models, right? And what we talked less about is the data, and it's something that I think that we should perhaps have another lecture series on, and really something that I think is very, very important to understand, and it is a complementary perspective. And as we think about the new frontier of AI, we also need to think about the new frontier of data, because they go hand in hand. All right, so that's that. Thank you very much, and feel free to go onto the website for updates and more material. Questions?
Yeah, regarding the future of data, and regarding this this vision in terms of how data relates to internet and to DNA and to intelligence overall, how does synthetic data fits into this vision?
Good question. It's a great question. So, I mean, in some sense, right, self-supervised learning is a lot about synthetic data, right? Because we do these fairly strange, easy things, right? We add noise. That's like creating synthetic data, right? We try to, replicate this process of going from an outline to details. We cannot do it because it's too expensive to do it, from a human perspective. So we add noise instead. We're like, oh, maybe we can just add different levels of noise to get at the same kind of perspectives, right?
I mean, like, for instance, there is like a digital twin of some system, right? And we generate data out of this digital twin and utilize this digital twin, the data from there to train the model. Or we have another AI model that's generating data to train the model that is implemented with different techniques. I mean, this kind of synthetic data. Does it mean these AIs are intelligent?
Sorry,
does it mean these AI are kind of a part of new intelligence because they are able to also generate data and train on itself?
Yeah, that's a good question. Because if it's data, that means, because also when I think about synthetic data, I think about, so in AI we still use it, right? It's like to prove a certain perspective, right? We create some data that we as human beings design, right? To be like, well, how well is this model able to count? And we create a lot of synthetic data by just putting different, geometric figures, right? And we try to replicate something that we as human beings, to test models or to train them a little bit. Yeah. And I think that you're talking about now perhaps about how that AI can generate data for other AI to learn from. That's what we saw here as well, right? And that we use a pre-trained image embedder to create these latent vectors where distance corresponds to our human understanding of distance. So then perhaps also that's like some kind of distillation process where actually we're able to distill this knowledge to a different model. And definitely distillation is also something that people do a lot, right? To maybe you can take a big model that knows something, you can distill that information by letting it generate data to train from that, and you can maybe focus on some aspects that are more important, and you can make the model smaller in that sense. Maybe you want to, or maybe give more examples of what were you thinking about?
No, I think that sounds really great.
Yeah, but I do think, right? I do think, and it's very interesting because I do think that as we go and make advances in these areas, we get less and less of that in some sense. That we have one single model that doesn't have to distill and use other models, right? Because that's the thing here. Like, it is expensive that you train this autoencoder using another pre-trained model where it understands images in some sense. Because, there's also like, if you can generate images, you can probably also embed them, right? It's just kind of a reverse process, but the architectures right now are not flexible enough, and we still, we want to squeeze out the most of the performance, we just throw everything at it. But I think as we proceed, it just becomes more and more a single model that does everything.
Yeah, but it's like probably when like for instance, we want to model understand what a sum is. I mean, what the concept of summing to integers, for instance. Not specifically, we can't easily say to it, right? It's not an algorithm. We can't code the model. We need to generate synthetic data for it, so it kind of from it gets this concept of summation.
Yeah. So right, but I see what you mean. That's interesting as well, right? But Right, so we can generate data because we have designed these computers or ourselves that know math, right? And sums, and we can feed it to a computer and it learns it, right? And I think, sure, right, because that's what neural networks are not very good at big sums, and we human beings aren't good at big sums, that's where you calculators, but still we teach kids, using examples and that's the basic set of data. Like a math book is sometimes data to see examples and learn from in some sense, because we want people to be like, well, you don't naturally learn about math by yourself. We're going to force you now to look at this synthetic data to build those skills still, because they turn out to be useful. And then we can, of course, debate how useful they are, for example, because maybe we don't need those skills because now we have calculators, but still at some level we want those skills in some sense, right? So maybe that's the correspondence that, yes, synthetic data is important, and right, we as human beings can make decisions and say like, well, you should focus on this right now to get better at this. And we can definitely imagine a future, for sure, right, where AI becomes super, super smart, and they also create synthetic data to train, their own offspring, if you will, to just learn things, right? Or say like, hey, I want this AI to have certain skills, and I'm going to create synthetic data to encourage that in some sense, so it can go on its own, right? In some sense, a dog. If every dog was as intelligent as a human being, right, know all these different things, it would be very, very hard to have them as pets, right? Because maybe they would want to do their own career and whatever. So maybe like it's also useful that we can create synthetic data for dogs to learn how to be disciplined still and do what we tell them, right? And they can be our companions and solve different tasks for us at a level that's useful. And maybe that's also what's going to happen. Like, yeah, synthetic data is a good way to encourage skills and and teach somebody something. Yeah, for sure.
Another question, which is more practical one probably. So, like, considering that the topic around it is super hot and like, there is a lot of research getting out like every day, and a lot of new techniques are being created. For Stable Diffusion and ChatGPT, what do you recommend basically thinking about pre-training the model to solve some downstream task, or would you just think about focus on fine-tuning at max?
Great.
That still, like for instance, like at Stanford, right, this center created this biomedical foundational AI, right? And it still works better for biomedical applications rather than if we get back to, like, say, GPT-3. And there are also for alternatives to Stable Diffusion, there are lots of algorithms trained specifically on some subsets, right? But that also perform sometimes really great for this particular downstream task. But considering that all this is changing super quickly, plus techniques changing, plus the model changes, would it be still rather better to fine-tune what we have already pre-trained, if we are not constrained with resources, of course?
That's a fantastic question, actually. So, yes, I think that's why also I talked about data today, because like if you want to do this yourself, understanding what data you can apply this to that somebody else hasn't, right? Find your own niche in terms of a data place where you can fine-tune the models, fine-tune and combine them in some sense. Maybe it also requires training something from scratch in some sense and combine it with these intelligences. So I think that's why, like, yeah, this technology is cool, but now you want to use it. Like, what data can you find and what small part of data, whatever that you can be competitive? Like, Stanford can do bio data in some sense, and they still outperform ChatGPT because that's not open data, perhaps, and Stanford can build us a great database and have a lot of domain expertise and add that nuances, right? Like we saw now for Stable Diffusion, there's a lot of different nuances to make it work great. There's different nuances and applications and details that will matter in creating, scans or X-rays, right? So if you want to do that, you should be, become there in some sense. And then, of course, so I think that's, and then, of course, that's like kind of still dangerous because then you need to, protect yourself by owning this data in some sense, right? And that you cannot replicate this. And because at the very end, right, I think that what we talked about before, I think that it is very centralized and winner takes all because well, maybe Stanford starts focusing on biodata and ChatGPT focus on everything around and all the biodata it can get. But there is synergies behind biodata and other data, like healthcare data, I don't know, whatever, right? And it gets that as well, and it gets more and more data, and it's more useful because it gets all the synergies in some sense. So it is very hard to cut off a small piece of the data space and just be like, this is mine. But if you can, I think that's definitely the future. Like, how can you be like, well, this data that I have here is not part of the internet. This is where I can be the expert and I can contribute. And if anybody wants to build a real intelligence, they cannot just go to the internet. They need to come to me in some sense. That's why I have a advantage, because I can take all the different models that OpenAI releases or see people put out. You can incorporate it, but you will be the one that can fine-tune it and make the best out of it in your domain area.
Yeah, and data is probably not that dynamic, right? And techniques and how the model is built and how the model is trained. Like the day before yesterday, there was flood, right, for T5. And I mean, it's kind of changing every day, but the data is static, right? That's what you're saying.
Exactly.
And it's like always your, for any organization, it's always your IP basically, right?
Yeah, and right, I think that better solutions give better data. So people start now, for example, like that's what I talked about last lecture as well. I mean, Google is not afraid of ChatGPT because of the technology. They're afraid now because this is being adapted, and that ChatGPT collects, 50 million data points per day. Like that's what gives them the advantage, right? It's the data and stuff. That's why, like, if Stanford starts incorporating these things into bio applications, you also get more and more data and better data, right? They can apply these solutions in a way that they also collect better data, right? Better solutions also collect typically better data, and this is kind of reinforcing, almost like a what is called composite interest, right? Like, it adds and adds. So yeah, I think understanding the data is extremely, extremely important, but also you cannot understand the data unless you understand the technologies as well, because they go so hand in hand. So typically, I think you need to have both, and I think there's way too many startups now. It's like, oh, ChatGPT is cool, we incorporate ChatGPT in whatever we're doing, but they don't have an understanding of what's going on, and they're going to be out-competed very soon, right, by somebody does something more general and better. Because now people are like, oh, ChatGPT is out, let's use it to just do this thing. Like, let's just use it to outsource work to cheaper labor, right? But like, that's not enough. Like, it's gonna work now, maybe before, big, before, because it's so new, you can start doing it and then maybe get some traction. But you need to think about carefully how to maintain your competitive advantage and really establish yourself.
No, but it still works for prototyping, because without resources you can still kind of prototype something. But yeah, I see what you mean. Yeah, definitely. And if you don't have an idea of the next step, right? Like somebody just can come and just do the same thing.
Exactly. So in our startup, right, I think there's this real interesting synergies as well, in my understanding, like between data and application. So we train from scratch using our own self-supervised learning algorithms that we haven't even covered here, right? It's like works extremely well for the things that we care and are experts at, right? So then we get data and understanding of the data in this expert area that we care about, and we also develop better and better algorithms that works better and better there, and they kind of reinforce each other, and it's a really, really fascinating interaction in between, in some sense, that I think is going to be a really key understanding now when you sort of kind of very transformative technologies and perspectives.